motors and drives and all that. Okay, so we have covered some portion of conventional space vector PWM, and we have understood how to implement the conventional space vector PWM. Then we have seen what is the maximum per phase voltage that can be applied for a given DC bus voltage if we go for the conventional space vector PWM. And what's the reason behind that, that also we have seen. So the inner circle touching the boundary, that's the limit for the PWM. So we have, okay, I think the next figure. Yeah. So this inner circle touching the boundary, that's the limit for a space vector PWM with linear modulation zone. If you cross this boundary, then you are going into over-modulation. The limit of over-modulation is when we start moving along this boundary of the hexagon. That is where we are operating in 6-step mode. That's the boundary. So we are applying only one vector for 60-degree interval. And that is what we have seen is basically the 6-step operation. That's the ultimate limit of any converter. So space vector is inclusive of all the PWM techniques. So basically we can express every PWM technique in terms of a space vector PWM. However, the other way around is many times not possible. If you want to express or want to have equivalent of a space vector PWM using sine triangle PWM or using any other PWM, that may be sometimes difficult. So we have seen that although we are applying the same vector sequence and everything is similar, still the sine triangle is having only utilization of 50% for the DC bus voltage, whereas the space vector is having VDC by root 3. The reason being that we are equally dividing the zero vectors for the space vector PWM. What is the meaning of that? The meaning of that thing dividing equal 0 times for the zero vectors is basically we are having equal height for these two waveforms, which is otherwise not possible. So if we consider say RYB, we have to fulfill the condition MR plus MY plus MB equal to 0. It's a balanced three-phase system. So unless you add any common mode, it's not possible to have the height of this triangle and height of this triangle to be equal. That's not possible, which is basically dictating the time interval TZ1 and TZ2. So we need to add some common mode, and by adding common mode, what we are trying to do, whichever length is, let's say, larger, we are trying to reduce that. So this length is, let us say, larger. So we are trying to reduce that. So which means we are bringing down this MB slightly. And this length is little bit smaller. This time duration is little bit smaller. So we are trying to increase that, which also means that we are bringing down our R. And because it is common mode, so it is added to all three. So it's added to Y also. So the red waveform what I have drawn over here is basically this common mode added modulating signals. So we have seen that in every sector we have condition for the three-phase modulating signals. Always, like if you try to have any sector, if you try to see, what you will find that always there is one modulating signal which is highest, another which is lowest, and another one which is in the middle. This condition is always true, universally for all the sectors. So every, say, from 90 to 210, we are seeing, sorry, 90 to 150, we are seeing over here this sector 1. So here R is maximum, B is lowest, and Y is in the middle. And this is true for the different modulating signals always. So then we can in general say that, yes, I will have modulating signal which will be having the maximum value, say M max, and I will have modulating signal which will have minimum value M min, and the third modulating signal will be in the middle of both. So that is called M mid. So I am adding my common mode to these three modulating signals, and the resultant is this star, M max star, M mid star, and M min star. So the meaning of this is the common mode is added not on basis of say just one modulating signal, but it is given on the basis of which sector we are dealing with, or which one is maximum, which one is minimum, which one in the middle. That is the criteria for adding or choosing the common mode. So when I say M max star, it is basically M max plus the MCM, the common mode. Similarly, M mid star is basically M mid plus the common mode, and M min star is basically M min plus M common mode. And this is universally true. There will always be one modulating signal which is maximum, another one which is lowest, and the third one which is in the middle. Now, what we are trying to do is that we are trying to make these heights equal. This height and this, what you see over, okay, I'll draw this. Let me take green color. So this height and this height we are trying to equate. And as a result, what we will have from similar triangle, if you see, these two widths will become equal. So that's what we have done in order to make TZ1 equal to TZ2, which means in order to have equivalent of space vector PWM in sine triangle PWM. Actually, it should not be called sine triangle PWM because we are adding some common mode. It is some, you can say, triangular carrier based PWM. So equivalent of space vector PWM, conventional space vector PWM and triangular carrier based PWM is what we are trying to get. And this is the condition we are equating. So we can simply equate 1 minus M max is equal to 1 plus M min. So that's the difference of the two heights. And this is the condition we are getting. So this exactly says that basically your M max star and M min star are equal and opposite. That's the meaning of this equation over here. M max star plus M min star equal to 0. That's the only condition for which this equation will be satisfied. And then you expand this and you will find that M common mode is basically nothing but minus half times or minus 1 by 2 times M max plus M min. And because we have the condition that we have three-phase balance system, so M max plus M min is equal to minus of M mid. This is always balanced. There is no star here. That's the original modulating signal what we have. So we can replace this with M mid also. So always we need to identify which is the modulating signal that is coming in the middle and take half of that and add to all the modulating signals. That's the common mode. So for example, if you talk about sector 1, in sector 1 what we have the Y phase modulating signal which is coming in the middle. This kind of linear. So you take that, take half of this and add to all. So that's why you will see that common mode is always looking like this, like a triangular wave. That's what we are actually getting. So this is what we have as common mode. So one or the other modulating signal will come in the middle and half of that we are adding, which is what I have shown yesterday. So that's the nature of the modulating signal what we are getting. This is nothing but half of what is coming in the middle. And if you add that, your modulating signal, the original modulating signal is changing its shape. This is not a particular harmonic. This is sum of all the triplet harmonics 3, 9, 15, 21, etc. and so on. And which is what is giving the resultant of this. Now, this has advantage in terms of utilization of DC bus, VDC, as well as current ripple. So what we were getting from third harmonic injection, we were getting either of this. If you add K by 6, you will get the maximum DC bus utilization. If you add K by 4, you will get best current ripple. But here when we have the conventional space vector PWM, we add the common mode. Both the properties are achieved together. We have the best DC bus utilization, which is 0.577 times of VDC, and we have the best current ripple. What can be achieved after addition of any common mode, third harmonic common mode? So this equivalent of is conventional space vector PWM will have both the properties. Now, why current ripple is improved, that we will see today. Fine. So this is clear to all of you, right? How to get conventional space vector through direct application of the vectors and then using the triangular carrier. These things are clear, right? Yes or no?
Yes, sir. Yes, sir.
Okay, little bit you need to speak because here we are going to do something interesting today. Okay, now ultimately what I have basically a sector, let's say ultimately I have this sector which is having vector 1. Say I'm talking about sector 1. And which is having the vector 1 plus minus minus, vector 2 plus plus minus, the 0 vector minus minus minus, and the 0 vector plus plus plus. Fine. We have said that conventional space vector PWM is basically applying sequence like 0, 1, 2, 7 or 7, 2, 1, 0. In triangular carrier based PWM, we have also encountered something called as bus clamping. What is the meaning of bus clamping?
Sir, in a particular segment, there is no comparison.
Correct. If we talk about the triangular carrier, what we were having the modulating signal, and we added a common mode such that it is clamped to the highest value, which is say +1 or -1 near the peak. So it changes its shape and the common mode is added and it looks something like this. So by clamping, what we are doing that when R phase, let us say this is clamped to the highest value, which means my VRO is also fixed to plus VDC by 2 for this duration. And here it is fixed to minus VDC by 2. That is the meaning of clamping. There is no comparison happening with the triangle. It's at the peak. So when it is highest, which means what? The value of VRO is fixed at plus VDC for this duration. And VRO is fixed to minus VDC for this duration. So how can this be done in a space vector PWM? What is the meaning of that? Basically, we are keeping the value of VRO to plus VDC by 2. That means that we are keeping the R phase at plus.
Sir, I have one doubt, sir. Here, sir.
Little louder, Ashish.
Sir, I have one doubt, sir.
Yes, yes.
Sir, in the overmodulation, in a particular segment, there is no comparison.
Yes.
And also in the bus clamping also, at a particular segment, there is no comparison.
What is the difference between the two?
Yes, sir. Is this two same or in different?
No, these two are not same. See, bus clamping we are achieving through addition of some common mode. We are adding some common mode which is equivalent to the difference between this. So we have seen some common mode which is going like this in case of bus clamping. And note that this common mode is occurring again at a frequency which is 3 times the fundamental frequency, which means this is not going to appear in the line-to-line voltage or line-to-neutral voltage. So in a way, although we are clamping it here, but we are maintaining the linear modulation, which means still our VRN is proportional to our MR, or we can say VRN is still MR VDC by 2, because in VRN this common mode will get cancelled. You understand my point? The average value I am talking about.
Yes, sir.
However, in overmodulation, when we are crossing this boundary, let's say we have the modulating signal which is way too high than the triangle. Triangle limit is here, let us say. We have crossed the boundary, which means what? there is something which is not coming as common mode, which means it is going to appear in line to line voltage also, line to neutral voltage also. And so here we have lost the linearity. This relationship is not true here.
Yes, sir.
That's the difference between the two. Although we are having the same effect on the VRO, but this is the difference. By adding common mode, we are ensuring that we do not miss the linear modulation. Whereas for the over-modulation, we are bound to lose the linear modulation. You cannot say that your VRN is proportional to MR. It's not. It may not be.
Yes, sir. It is true, sir.
Correct?
Mm-hmm.
Now, the same thing we are trying to understand from the space vector point of view. Now you see what we are basically applying. Okay, let us be here itself. Okay, we are applying 0, 1, 2, 7. What are the vectors or the state? This is minus, 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 plus, minus, minus, plus, plus, minus, and plus, plus, plus. The meaning of bus clamping is that R will get clamped to plus VDC by 2, or R will get clamped to this state which is plus. So which means that if you don't apply 1, 0 state, which is this 0, minus, 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 if you don't apply that, just keep your vectors confined to 1 to 7 or 7 to 1, then R phase is not switching. It is only plus always. You understand my point?
Yes.
Yes, sir. Yes, sir.
Yes, sir.
So in this sequence 0, 1, 2, 7, we have removed this. And effect is that we are having plus minus minus, plus plus minus, plus plus plus. See, Y has switched from minus to plus, B has switched from minus to plus, but R is keeping the same value. This is the meaning of bus clamping in a space vector, that our R phase is not switching, it's keeping at the maximum value. Similarly, instead of 0, 1, 2, 7, if you take only 0, 1, 2, let's say minus, 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 plus, minus, minus, plus, plus, minus, that's all. You take these three states. Now what will happen? Your R is switching, Y is switching, but your B is clamped to minus, minus, minus. So by having this 1 to 7, you are clamping your R to the positive DC bus. And by having 0, 1, 2 only, you are clamping your B phase to negative DC bus. You understand my point? Always one phase is going to remain clamped. That we know, because every 60 degree we are having the clamping. So if R is clamped here, before this, we will have B which is clamped over here. Then we will have Y which is clamped over here. So every 60 degree this will have continuity. It will keep repeating itself. Understanding my point? So little more closely, if we try to understand from the space vector point of view, what do we have in a space vector? We have these vectors, say plus minus minus, plus plus minus, minus plus minus, minus plus plus, minus minus plus, and plus minus plus. Correct? And the zero vectors are here, minus minus minus, plus plus plus. I have told that these axes or these vectors basically correspond to one of the peaks for the three-phase modulating signal. Say, for example, if you take theta equals 0 degree over here, this means that this is corresponding to 90 degree angle, which is basically R phase peak. So if this is R phase peak, positive peak, then this is R phase negative peak, just 180 degree apart. Then we have from this, if you go 120 degree, this is basically Y phase positive peak. And then opposite is Y phase negative peak. Then here we have B phase positive peak and B phase negative peak. So any modulating signal can be clamped near its peak, which means if we draw the middle lines for all the sectors, we will have clear boundary for which we can say that we can clamp the phase. Let's say we are talking about 60 degree clamping. So 60 degree clamping is basically what? We are clamping our R phase to positive for this duration, 60 degree to 120 degree. Here R phase is clamped to positive and you go on in sequence. So basically this corresponds to this zone. From 60 degree to 120 degree, you are clamping the R to positive, which means in this zone, you will never apply the zero vector. Minus 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 will not be applied to this zone. This is strictly not applied. So if you do not apply this vector 0, which is minus minus minus, then your R will remain positive throughout this zone. So one example we have seen that the one option is 7 to 1. You can apply this in this half, in the sector 1. The first half you can apply 7 to 1 always. Then in sector 6, similarly you can apply 7, 6, 1. 0 is not applied. So if you don't apply 0, what will happen? Your R is always going to remain plus for this zone. This is basically corresponding to your 60 degree clamp, what we have seen in the sine triangle or triangular carrier PWM. Similarly, what we will do, we will have this zone where B is negative. So what I will do? B is negative means I cannot apply the vector 7 plus 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 cannot be applied in this. So we have to work with only zero vector 0. Minus minus minus. So what sequence I can have here? 0 1 2. If you have 0 1 2, your B is always negative. And similarly here 0 3 2 or 2 3 0, whatever order you want to keep. But the sequence will remain like this. Then again, alternatively, what you do, you apply only 0 vector 7, which is plus 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 in this zone. So what will happen? Your Y will remain clamped to positive. So the options would be 7, 2, 3 and 7, 4, 3. This is the sequence I am saying for the sample what we have seen yesterday. For that sample, instead of applying 0, 1 to 7, you are applying only a portion of this, a fraction of this, either 1 to 7 or 0, 1, 2. Then again you go on for the next. So here your R is clamped to negative, which means you cannot apply the 0 vector 7, which is plus plus plus. R has to remain at 0. Sorry, the minus. So you can apply something like 0 3 4 or 0 3 5. Sorry, 0 5 4. Correct? Then similarly in this zone you can apply only one zero vector, which is 7 plus plus plus, so that your B remains clamped to plus. Then our options would be 7 4 5 and 7 6 5. Correct? And then here we can have only zero vector, which is 0, because we are trying to clamp our Y phase to minus. So then our options would be 0, 5, 6 and here it would be 0, 1, 6 or 6, 1, 0. You can have the other way around also. Instead of 7 to 1, 1 to 7 is also fine. And actually you need to do to avoid multiple switching. If one of the samples you are applying 1 to 7, you can continue with 7 and come back to 1, 7 to 1. Then again you can go back to 1 to 7. So you have to go alternatively. This rule remains same. You cannot have multiple switching for the consecutive samples. Understand my point? This is 60 degree clamping. The same effect what we were getting from this common mode addition, now we can get with this application. You don't apply. So what will happen? 0, 1, 2 is there. So what we are basically doing, we have computed T1, T2. Now what we are doing, we are applying 0 for the complete duration Tz. Then we are applying 1 for duration T1, 2 for duration T2. That's all. Or 7 to 1, we are applying Tz for full duration. this vector 7, and then T2 and then T1. There is no other 0. So 0 vector is not divided at all. It's applied only once. Correct? Understand my point?
Yes.
Okay.
Yes, sir.
Similarly, you can also work out if, let us say, we have the, instead of continual clamp, we have to go for a split clamp. What a split clamp is saying that instead of having clamping in the middle, we are doing 30° here and then 30° here. So that will change the sequence slightly. Now, if you want to have R phase not switching between, say, 60° and 90°, okay, and 90 to 120 you are keeping silent, you are having the normal whatever comes after the common mode addition, and then again from 120 you are applying this to 150. Here you are not switching your R phase, which means what? What is the meaning of not switching the R phase or keeping it clamped to the positive?
No comparison.
Not use 0.
Yes. Which 0 vector we cannot use? We cannot use 0 vector 0. That's the meaning of clamping the R phase to plus. Okay, now this we are doing for the range, which is split in two parts. So this is 0° line, then 60, then 90. So what we are doing, we are going from 60 to 90. Here my R phase cannot switch. That means I have to apply only one 0 vector, which is 7 in this zone. So option could be 761. And then I am keeping the same thing for this zone. Here also I am keeping my R phase to positive. Here also R phase to positive. Then again I cannot apply 0 vector 0. So option is only 7. So 7 to 1 is the option for this. If you go in this manner, like write for all the three phases and keep applying the vectors, then this will result into something which is called as split clamp or 30° clamp. 30° split clamp. These are all the names for this bus clamping PWM, which normally we have seen for the sine triangle PWM. You understand my point?
Yes, sir.
Understand my point, right?
Yes, sir.
Now, see, it's not necessary that we have to have only this kind of sequence 1 to 7 and a subset of that. It's not necessary. We are free. No, here when we have to apply vectors, we can apply any vector. Say, for example, I can do 1 0 1 2 instead of 0 1 2. So what I am doing basically, I am splitting my active vector 1 in two parts. I am first applying the active vector 1 for duration t1 by 2 and then applying the 0 vector for time tz, and then again the active vector 1 for another t1 by 2 and then the active vector 2 for time duration t2. What's the problem in this? No problem. Why? I am not violating any rule. So one thing what I had over here in case of clamping, when I am missing one of these states, basically the effective switching frequency is 2/3 of the original switching frequency, or we can say switching frequency is 2/3 of the carrier frequency. Of course, because now we have only two switchings in a sample. Understand my point? So when you clamp, well, let's say split clamp or this 60° continual clamp, your switching frequency is basically coming down to 2/3 of the original. Original means the conventional space vector PWM if you take. Compared to that, it will become 2/3. Because instead of 3, we are having only 2 switching per sample. Now, when I have something like this, say 1012, I have come back to the same switching. The FSW is same as conventional space vector. Again, I am having 3 switching. Then what is the advantage of doing anything like this? You understand my point?
Yes, sir.
You understand the question here? I can make any sequence. Let's say not just this, I can have 1 0 1 0 1 2 or anything like 7 2 7 2 7 2 1. I can have anything. There is no problem in that. What I'm doing effectively, I'm having more switching. That's fine. But other than that, what's the advantage or what's the problem or what are the issues that we will see? This is hidden in terms of when you start doing the current ripple analysis. What is happening from conventional to bus clamping and to this kind of sequence, which is basically called advanced bus clamping PWM. We do have the bus clamping, but this is one step ahead. This is advanced bus clamping PWM. So sequence like 7-2 or 2727, okay, 727, 2721. This is also part of advanced bus clamping PWM. You understand my point? And some of these things cannot be achieved through sine triangle PWM. If you like, can be achieved, but it's not so straightforward. If you try to have a triangular carrier and try to add common mode, this may not be possible to get in a very straightforward manner. You understand my point? Because you cannot switch a phase twice within same sampling period. You understand what I'm trying to say over here? If you have the carrier, you have the modulating signal going here, it can only switch once in this subcycle. You cannot have the phase suddenly changing from here to here so that it can have another switching or another switching here. That's not very straightforward, right?
Yes, sir.
Yes, sir.
So these things where our active vector is switching twice is something which is difficult to achieve through the carrier-based PWM. Now, what are the advantages of these? We will see. But first, let us see some rules. Some rules we will set for if we are forming any vector sequence for ourselves, then we have to keep certain rules in mind. We cannot just randomly apply any vector anywhere. So symmetry and other things has to be considered over here as well. We cannot just randomly keep on going. Now, rule is that we can have only one switching at a time. So this is what the sequence we can have. We cannot violate this. If I talk about sector 1, then I have vectors which are basically located in space at different locations. What is meaning of this is basically that you have these vectors over here, minus, minus, minus and plus, plus, plus at 0. The rule says that if you want to maintain the waveform symmetries, we know that VRO 180 degree plus theta is basically minus of VRO theta. This we know very well, right? Same for VYO 180 degree plus theta is minus of VYO theta, and same for B. Which means what? If we are applying any vector at any angle, say theta, and you go 180 degree away from that, the vector applied here should be opposite of what you have applied. Say you have applied vector 1 over here, which is plus minus minus, must apply vector 4 over here, which is minus plus plus. If you have applied vector 2 plus plus minus, then the next vector should be minus minus plus at this location, which is 180 degree away from this. You understand this point? So we cannot have very random applied vectors. This has to follow the rule, which is basically coming on basis of this half wave symmetry. Now we have three phase symmetry also, where we write that our VYO is basically VRO theta. The meaning of this is that if you are having any particular value of R at this position, say theta, your Y will also have same value, but at a location which is 120 degree apart from that or 120 degree away from that. You understand my point?
Yes.
Fine or not?
Yes, sir.
Yes, sir. Yes.
Okay, so if I combine these two things over here, what I will do, I can write like VRO 180 degree plus theta is basically minus VRO theta. So VRO 120 plus 60 plus theta is basically minus VRO theta. So now we know that, okay, maybe I need to write one more or a couple of more equations over here. So VYO 120 plus theta is basically VRO theta. Similarly, VBO 120 plus theta is VYO theta. And VRO 120 plus theta is basically VBO theta. We are maintaining the three-phase symmetry. Fine. This is understood to all of you, right?
Yes, sir.
Yes, sir.
Correct. Now this is what we place over here. VRO 120 plus whatever theta is there, that should be VBO theta, which means our VBO 60 degree plus theta is basically negative of VRO theta. What is meaning of that? The meaning of that is this is combined effect of these two rules. The meaning is that if you are applying any VRO, say here you have applied VRO which is positive at this point, then at 60 degree apart you can have only BO which is negative of VRO. So that's why this vector 2 has this minus over here. So if you have say plus minus minus, what will happen? And if you do work for other these equations also, I will write the complete condition over here. So this will be basically minus VBO theta and VRO 60 plus theta will be minus VYO theta. This you keep in mind. So whatever we are applying at theta for RO, YO and BO, this is basically coming in cyclic manner for BO, YO, RO. So what is the meaning of that is basically if we have applied this vector 1 at angle theta, then at 60 plus theta, I can have the cyclic. So Y going at place of R. That's what the meaning of this is. So Y will go here, B will come here and R will come here, but all will change their sign, which is basically vector 2, which is 60 degree apart. You understand my point? And again, if you go for another 60 degree, what you will find this coming at Y coming at R, this coming at Y and this coming at V. So minus plus minus. This is basically your vector 3, which will be at 120 degree plus theta. You understand this point? This is coming out of the symmetry which we have, three-phase symmetry and half-wave symmetry combined together. So if we are applying vector 1 at any location theta, then at 60 plus theta, we must have vector 2 applied. We cannot have any general vector. And if you do that, you will automatically ensure these two symmetries, the half-wave symmetry as well as the three-phase symmetry. You understand my point or not?
Yes, sir.
Correct? So whenever you are forming the vector sequence for any of your, let's say, general vector sequence or general application, let us say, you must have this rule followed from one sector to another sector. Basically 60 degree apart will be next sector. So at any location, if you have applied any vector, the next vector should be which is 60 degree away from that vector. If you applied 1 over here at 60 plus theta, you must have 2. If you applied 2 over here at 60 plus theta, you must have 3. So that is the meaning of the distribution. That's the meaning of maintaining the symmetry. So we see that this is automatically happening. If you have, let's say, conventional space vector PWM 0127, 7210, 0127 for sector 1. So now samples are coming at 10, 30, 50. Again, for sector 2, the samples would be at same location and it will become 7230, 0327 and 7230. So now from this 10 degree to next sector 10 degrees, basically we are 60 degree apart. Understanding my point? So instead of 1 we have applied 2, instead of 2 we have applied 3. And what about 0 and 7? You again write, you have minus 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 for 0. You change the locations, make it plus, and this also becomes plus. And if it plus plus plus, you change the locations, minus minus, and this becomes minus. So if you have applied 0, you must have 7. And if you have applied 7, you must have 0. These two samples are exactly 60 degree apart. And you see how the symmetry is maintained. This itself will ensure that you have half-wave symmetry as well as the three-phase symmetry. You understand my point?
Yes.
And this must be true. What we have seen over here, conventional space vector PWM, this must be true for any of your own PWM which you are trying to make. If you want to have good quality PWM with all the symmetries over there. Clear?
Yes.
Are you clear? Are you fine with this? Yes or no?
Yes.
Yes, sir.
So if now you are trying to make any vector sequence for bus clamping, say with 0, 1, 2 or 1, 0, 1, 2, what basically you need to do, you have to ensure this, what I have said over here. When you move from one sector to another sector, you keep your sequence such that this condition is met. And another condition is you must not have multiple switching at a time. You must have only one switching, or better continue with the same state. Correct? Fine here?
Yes, sir.
Yes.
Okay.
Yes,
Now,
sir.
one last point. What about something which is within the sector? We have seen across the sector what we are doing. What about within the sector? So that is what is relates to our quarter wave symmetry. Quarter wave symmetry we have not discussed so far for a space vector. Now quarter wave symmetry is something which when you translate to space vector PWM, it comes to symmetry about this 30 degree line. So when you have this middle of the sector, if you are having this say quarter wave symmetry to be maintained, then what we must ensure that say vectors 1, 2, 0 and 7, these are there. What we must ensure that if you travel 30 degree, theta on both the sides of this middle of the line, if you have applied any vector at this point, say 1, then at 30 plus theta, you should have the dual of that vector applied. Dual means these two vectors are dual of each other when we talk about sector 1. So if you have applied vector 1 at a point which is 30 minus theta, then you must have vector applied which is 2 for 30 plus theta. If you have applied vector 0, the dual of that is 7. You understand my point? Do you understand this point?
Sir, hello.
Yes.
Sir, we in quarter wave, like we take theta around theta peak, no, sir.
We take, but
Then,
this is I'm talking about that's
okay,
for
yes,
one phase, right? VRO
yes, sir.
90 minus theta equal to VRO 90 plus theta. But 90 is not the location for Y, right? 90 is not the location for B. For Y, it will become 210. For B, it will become 330. This I'm talking about the combined effect of all three phases in a space vector.
Yes,
So if you ensure that you have applied any vector, active vector, say 1, then at the corresponding 30 plus theta, you must have the vector 2. If you have applied vector 2, you must have vector 1. The dual of that applied at both the places. If you have vector 0, then 7 must be applied at the similar location. Say 30 minus theta is 0, then 30 plus theta should be 7. If 30 minus theta is 7. The 30 plus theta should have 0. You understand my point? We are talking about something as reflective symmetry. Now, for example, the conventional space vector PWM, which automatically maintains all the symmetries. You see here, this is the 30-degree line we have seen, right? You start moving on both the sides of this line. You see that if you apply 2 here, it is 1. If it is 7 here, it is 0. If it is 7 here, it is 0 here. If it is 2 here, it is 1 here. If it is 1 here, it is 2 here. If it is 0 here, it's 7 here. You take the sequence other way around. You start with 7 2 1 0 and continue in this manner. You will again see that quarter wave symmetry is maintained. Or this principle, what I am saying, the dual of each other is applied. Dual of each vector is applied. By dual, I mean there are two active vectors which are dual of each other. One is the beginning of the sector, another is the end of the sector. There are two zero vectors which are dual of each other. You understand my point? So if you are forming any sequence on your own, you must ensure this as well if you want to have quarter wave symmetry in your system. Correct?
Yes, sir.
Fine?
Yes, sir.
Yes, sir.
Good. So now we have understood that how we can make our own space vector PWM. Say for any advanced bus clamping or any other corresponding thing, we can make our own PWM. There is no need to follow only conventional. What basically we have to do, we have to apply the dual times properly. That is all. Nothing more we need to do. Fine? Is that fine or not?
Yes, sir.
Yes, sir.
Okay.
Yes.
Now, what is happening when we are having different vector sequences, say 0, 1, 2, 7, then 7, 2, 1, 0, then 0, 1, 2, or 7, 2, 1, or 1, 0, 1, 2, or 2, 7, 2, 1. These are different sequences when we are having. What is happening to the current ripple? Which one we should pick? Why we should pick? So this is where we need to do the current ripple analysis for the space vector PWM. How we do the current ripple analysis for per phase basis? We have taken the VRO, then we went for VRN, then we subtracted the average value. So basically obtaining the voltage error. That's what is the ultimate aim. And once we have the voltage error, we can integrate that over the time duration, whatever interval it is having, and that gives us the current ripple or current error. Fine. The only difference here we have is that instead of scalar value, we have the vector. So for example, if I am trying to have, let us say, I am trying to have the sample at 30 degree. This can be done for any angle basically. It's not necessary to have only 30 degree for analysis, can be done for anything. But for simplicity, I am keeping it like that. Say my sample is here at 30 degree and the sample is of this much length, let us say. Now what we have to do, we have to find the error vector, error voltage vector, what we have applied to the system. That's what is the ultimate aim. Then we know the leakage and we can compute the error vector or error in the current vector. So what we are applying, let us say first we talk about the vector sequence 0, 1 to 7. What we have vector Vs, vector V1, vector V2 and 0 and 7 over here. The error vector is basically what you are applying minus your actual. So you start with 0. When you apply 0, what is happening? Your error is nothing but negative of your actual voltage or negative of your what is the voltage vector which you are trying to realize. So you have an error which is exactly opposite of this. Say this arrow I have drawn. It's overlapping basically. Again, then you apply vector 1. Now what is the voltage error? Basically V1 minus Vs. So V1 minus Vs is basically this vector which is what is coming here. See the direction and magnitude both. Then we have voltage error corresponding to, say, I will name it for 0, for 1, and then voltage error for 2, which will be V2 minus Vs. So which is again here. And then finally for 7, again it will be overlapping this 0 vector. Now what we do the current ripple analysis on basis of these vectors, these error voltage vectors. And better way to do is we look for these errors in the synchronously revolving DQ reference frame. So what do we have in synchronously revolving DQ reference frame? We have the voltage vector which is lying along the Q axis. That's correct, right? Q axis is basically where the voltage is located along, and it is rotating with omega. Now D is something which is perpendicular to that. So I will draw it, say, somewhere here. So in a way, getting the ripple in this reference frame, say this is D axis, D is lagging behind Q, and this is where my flux will be lying, the DC flux. Now, in a way, getting the error along these axes is easier because this is something which is continuously rotating. So if we know the location at this point, we can draw the error in the current ripple at this location comfortably. So what we will have, because we have voltage error vector which is located along this line, so integration of that will also be extended along this line. That's the axis of the voltage vector, or the Q axis. Nothing but V error into T divided by L. So this whatever voltage vector you have got, error voltage vector, the scaled version of that. Then we have the vector, error vector corresponding to 1, which is coming somewhere here. So we will have a parallel line going like this. This is the error in current vector. And then we have this vector applied, vector 2. So we have the error which is along this line. So we will have error in the current vector which is moving along this. And because we are talking about ripple, it must come back and meet at this point. So for 7, this will be here. So these two lengths are equal because our TZ1 and TZ2 are equal. You understand my point? Understanding my point?
Yes, sir.
Yes.
Yes, sir.
Now, just one more thing I will add over here, and then we will continue tomorrow. I couldn't finish today. I thought I will be able to complete it. Now what we can do, basically, we can draw our T axis and Q axis current ripples. So we have the intervals, say TZ1, T1, T2 and TZ1. These are the intervals. Now what is the ripple along the Q axis and D axis for the current? So you see that for this vector, when we are applying 0, for first vector 0, it's moving along Q. That means the ripple is only moving along the Q axis, that too on the negative side. So which means Q will see a ripple something like this. Then when you apply 1, the ripple is coming back and going on the positive side of the Q axis. It's reducing along the Q axis and going slightly positive, the projection of this vector on the Q axis. So this is something like here. Then again we have 2, which is taking it further positive. So we can have something like this, taking it higher magnitude on the Q, and then finally coming back to 0, which is what is 7 is doing. So we have peak to peak ripple something coming like this. If you have this TZ1 equal to TZ2, these two peaks are equal because these durations are equal. Now for D axis, what is happening when you apply 0 or you apply 7, the error is only moving along q axis, which means there is no change on the d axis for these durations. It is changing only when you apply the active vector 1. So it's going along the positive d for some height, say here. So which means the ripple would be something like this, and then it is coming back to 0, and then it is staying here. So it is the q-axis ripple which is dependent on how you are dividing your zero vectors, say tz1, tz2. So for sine triangle PWM, tz1 is not equal to tz2, which is why these two heights are not equal, and that is why the ripple on the q-axis, the RMS ripple on the q-axis current is more for sine triangle PWM. Whereas for conventional space vector PWM, we have equal heights, which reduces the ripple compared to the sine triangle PWM. That's the reason why we have better ripple for the conventional space vector PWM compared to the sine triangle PWM. These heights are equal for conventional space vector PWM. Do you understand this point?
Yes, sir.
Okay, so I stop over here. I have taken some extra 6 minutes. So,
Sir,